So far in this subject, and probably in your previous studies in probability theory, we only looked at univariate distributions. And a univariate distribution, as the name suggests, univariate, one variable, describes the distribution of a single variable. And we had the two categories here. The discrete ones we were described by a probability mass function. That was a list of each possible outcome the variable could take and the probability of that happening. For a continuous case, we had to have probability density because there would be an uncountably infinite number of possibilities. But both of those categories, whether discrete or continuous, are just describing one variable, one outcome measure. In reality, or in handling more complex data sets and more complex problems, very often we want to describe a number of variables which are not independent of each other. That in fact, the movement or the changes in the value of one might affect the others as well. So we'll take a very simple example to start with. Doesn't get simpler than coin flips. So let's say we've got three fair coins. So they're 50-50, whether each lands heads or tails. And we flip all three and record the outcomes. So if I say X is the number of tails observed on the first two flips, X is a univariate random variable. Y is the number of tails observed on the first three flips. Again, this is one variable, a univariate distribution will describe it. But X and Y are not independent of each other because if I know X, it will tell me something. It won't tell me what Y is, but it will tell me what Y might be. And so I may wish to consider the joint distribution of X and Y. And this is the probability distribution characterizing the chance that the ordered pair XY takes a given pair of values. Notice I say ordered pair because X being 1, Y being 2 is not the same as X being 2 and Y being 1. So if this is discrete, I can have a discrete joint distribution, and that will just be a list of probability masses associated with all of the ordered pairs taking all of their possible values. For example, the probability that XY equals Mn. The probability that XY equals whatever else I wish to state. So keeping with our coin example, the range of X, the number of tails I could get on the first two flips is 0 or 1 or 2. So it's a set containing three elements, 0, 1 and 2. The number of tails I can get on the first three flips is of course 0, 1, 2 or 3. But I can't say that there's 3 possibilities for X, 4 possibilities for Y, therefore 3 times 4, 12 possibilities for the ordered pair X and Y. Because there's a few basic things here. I can't have more tails on the first two flips than I got on the first three. So Y can't possibly be smaller than X. Also, the difference between X and Y is the number of tails obtained on the third flip, which is 0 or 1. So X has to be either the same as Y or 1 less than Y. So although it looked maybe at first glance that 3 possibilities for one, 4 possibilities for the other meant 12 possibilities in total, a lot of those will be associated with a probability mass of 0. If we want to get to the joint distribution, of x and y. We'll start with just the univariate distribution for x. X is the number of tails on two flips of a fair coin, so it's a binomial with parameters n equals 2 and p equals 0.5. So that means I've got a quarter chance of getting 0 tails, a quarter chance of getting 2 tails, and a half chance of getting 1 heads and 1 tails. Now what we said on the previous slide was that x and y were related, and if the third flip was heads, then x equals y. The count of tails in 2 flips and the count of tails in 3 flips would be the same. Or half the time the third flip was tails, so it'll add 1 to the count, so then x plus 1 will be equal to y. So if we look at this joint distribution that we've written here, what I've done is I've effectively split the 0.25 associated with x equals 0 into half of that being associated with xy being 0, 0, and half of that being associated with xy being 0, 1. Then the middle category, the 50% of the time that there's 1 tails on the first 2 flips, I split that 50-50 with the outcome of the third flip. So a quarter of the time xy will be 1, 1, a quarter of the time xy will be 1, 2. And then the final category, the 25% associated with x being 2, splits into 0.125 associated with xy being 2, 2, and 0.125 associated with xy being 2, 3. So what we take from this is if I actually plot this up, and this is a visual which we will come back to over the next few slides and subsequent videos, is you can see well, you can't see, but you can probably visualize, imagine at the back, that there are 12 areas on there. There's 3 spaces up the x-axis, 4 spaces up the y-axis, 3 times 4 is 12. But I've got some which are zeros. There's no chance these 3 I can see flat at the front. No chance that x is 0 but y is 2. No chance that x is 0 but y is 3. No chance that x is 1 but y is 3. Similarly, there are other 0 probabilities at that back corner behind the 2 large red towers. I can leave you to figure out what they are.